Okay, one of the quantities that we have in chemical reactions is the energy. And we have here 3 units for energy. One is the joule, capital J, joule. This has a physics definition. Physics definition is 1 kilogram times meter squared per second squared. This is called a Newton meter. But we aren't going to worry about this much. It's just a unit or measure of energy. Another one is the calorie, which has a lowercase c, C-A-L. The calorie has a different definition. Rather than this physics definition, it has a definition that is, it's the amount of energy required to raise the temperature of 1 gram of water by 1 degree C. So that's a calorie. If we figure out the relationship between the joule and the calorie, we come up with this. 1 calorie is equal to 4.184 joules. It's not by definition. It's 3 bars usually meant by definition. It should be just 2 bars. This is to 4 sig figs here. We get more sig figs in this relationship. And then we have one more. Well, there's kilojoules and kilocalories, which are just related to that. But the last one is the calorie with a capital C. The calorie with a capital C is the food calorie. And so there are 1,000 chemical calories per 1 food calorie. So if you have something that was, let's say, 600 calories, a meal, 600 calorie meal would be 600,000 chemical calories. All right, so the first part of this is just doing interconversion. So if we have 42.5 kilojoules, how many joules is that? How many calories? How many kilocalories? So I'd probably go in that order. And so we just need the conversion factors for that here. You don't have to memorize this one, but you use a lot. Not too hard to memorize. 4.184 joules per calorie. One thing that you need to work on memorizing, though, if you haven't done so already, is nomenclature. You know, the nomenclature is like formulas and that kind of stuff. You know, the next test is going to have some chemical reactions. And if you can't write the formula, the correct formula for the chemical reactions, you're going to lose a lot of points. So what you want to do is you want to just whatever way you can figure out how to memorize things is good. You might go online and see about certain memorization techniques, whatever works for you. Okay, so anyway, this you don't have to memorize. And so we have 42.5 kilojoules. And so kilojoule would be abbreviated lowercase k, capital J, kJ, kilojoules. Probably the easiest is just to do a kilojoule to joule conversion. 1,000 joules per kilojoule. And so this gives me 42,500 kilojoules. Or not kilojoules, sorry, joules. 42,500 joules. All right, if I have 42,500 joules, then we can figure out how many calories that is. 1 calorie is equal to 4.184 joules. So what does that come out to? Do the calculation here. $42,500 divided by 4.184. Oh no, not 100. 10,157.7 calories. We're only allowed 3 sig figs, so we might call this 10,200 calories, which is equivalent to 10.2 kilocalories. Just move that over. 10.2 kilocalories is the same as 10.2 food calories, with a capital C. So those, we would write that in scientific notation. This was a book did. All right, so those are unit conversions. Now, when we use these in stoichiometry, then we're going to have this, delta H. Delta H is a change in enthalpy. H is enthalpy. Some reactions are exothermic, they give off energy. Some reactions are endothermic, they consume energy. So exothermic reactions produce energy, endothermic reactions consume energy. There are two ways to represent this. So let me skip this, most of this slide, just go right to the two ways of representing this. We have a sign convention like minus 2,855 kilojoules, you'll see it there. That minus is like, let's say you have minus $10. If you have minus $10, what does that mean? You owe $10. You're going to lose $10. That's it. Is there such thing as a minus $10 bill? Is something like that? Maybe you gain a minus $10 bill. Can you gain a minus $10 bill? No, you lose. And so energy is like money. There's no such thing as negative energy. You know, you only have positive energy. The negative sign is just to indicate which direction it goes. Like, if it loses, it's minus. If it gains, it's plus. That's it. And so the convention here is this. For exothermic, we put a negative. That means it loses. The reaction produces energy. So when we look at this reaction, this is ethane plus oxygen. So this is combustion of ethane, forms CO2 and water. In the combustion process, it also forms some energy as well. So this reaction loses energy. That is, it produces energy. How much energy does it produce? It produces positive 2,855 kilojoules. And so these are the two ways. If we write it inside the equation, you know, the energy term is always going to be positive like this. The only difference is which side. When it's negative like this, it's on the product side. When it's positive like this, if you look at delta H here, this is the change in enthalpy or change in energy. It's plus 92 kilojoules. That means that 92 kilojoules is on the left side, the reactant side. So this is the sign convention. Energy is always positive. We just use the sign to keep track of which direction the energy goes. And so even though this bottom equation is much more convenient because it tells us it's produced here, it's rarely written like this. Mainly it's written like this, top equation here, so you have to know that. In this endothermic reaction, it's not written like this, it's written like this. So you can see the sign here. Now delta H is just kind of the change. They say delta H is the heat content, or enthalpy is the heat content, but heat is we usually think of as being transfer kinetic energy, you know, from hot bodies, high kinetic energy, to cold bodies, low kinetic energy. But this is a little bit different. This is a combination of both, you know, kinetic and potential energy in here. We aren't really going to get into it that deep. All right, so let's look at the thermal decomposition of limestone here next. Limestone's pretty stable, unless attacked by acids, but one thing is heat, very high temperatures. So calcium carbonate solid can decompose under extreme temperatures. Heat. It forms solid calcium oxide, so they tell us it forms, and CO2 gas, carbon dioxide. Yeah. This is an endothermic reaction requiring 178 kilojoules per mole. And so delta H for this is 178 kilojoules. They write a little R here. R just means reaction, but this R you don't necessarily have to write, because if I write a delta H here, this delta H is associated with this reaction. And so it says 178 kilojoules per mole of calcium carbonate decomposed. So this is 178 kilojoules per mole of calcium carbonate. when I decompose 1 mole of calcium carbonate, I'm going to consume that amount of heat or produce that amount of heat. I'm going to consume it because it's positive. It's endothermic. And so what that means is for every mole of calcium carbonate solid, I'm going to need at least 178 kilojoules worth of energy to decompose this into calcium oxide solid plus CO2 gas. And so these are the two ways of representing the thermochemical equation. And the top way is not the typical way it's written. The typical way it's written here is like this, or delta H equals plus 178 kilojoules. They don't write per mole because what they do is they do this. They associate this with this equation. So when I look at this equation, I have 1 mole of calcium carbonate. So that's 178 kilojoules per 1 mole of calcium carbonate. But I also have other things. Like for example, if I wanted to produce 1 mole of calcium oxide, I'd need 178 kilojoules. If I want to produce 1 mole of CO2, I'd need the same, 178 kilojoules. So that energy is associated with this equation as written. And so you can see it here. These we just use this stoichiometric ratio, 1 to 178 to 1 to 1. And we can come up with mole ratios. And so I might be interested in the CO2 produced from this. So if I'm interested in the CO2 produced, then I could say that there's 178 kilojoules per mole of CO2 that's produced. And so it doesn't have to be calcium carbonate. Since it doesn't have to be calcium carbonate, then oftentimes it's left blank like that. So you can see here it's left blank. This. And then we just do whichever one we want. That's the first way. This is the second way. The second way is only done in Chem 4. Okay, well, now we're going to do thermochemical stoichiometry. We can do stoichiometry because this is just another stoichiometric ratio here. And so what we're going to do is we're just going to go from moles to energy. So for example, if I want to decompose 2 moles of calcium carbonate, to decompose 2 moles of calcium carbonate, I'm going to need twice as much energy. And so to have to double this. 3 moles, I'd have to triple this. So that's our stoichiometry. So what we can do is we can go straight from moles to energy. Normally we go moles to grams. Here we're going to go moles to energy. And the conversion factor that we're going to need is delta H. So let's take a look at this problem. What mass of liquid N-octane, CH18L, a component of gasoline, must be burned to provide 9.05 times 10 to the 4th kilojoules of heat? Here they tell us, delta H for this reaction, this is the way we read it, delta H of reaction. Delta H of reaction for this is minus 471 kilojoules per mole of CH18 burned. So what they want is what mass of liquid octane. All right, so what we're going to do is we're going to go from kilojoules here. We got 9.05 times 10 to the 4th kilojoules. We're going to go from kilojoules to moles of, we can go straight to moles of octane. And then from moles of octane, we'll go to grams of octane. To get to kilojoules per mole, we'll need the delta H. And so I'll do 9.05 times 10 to the 4 kilojoules worth of energy. How much octane has to burn? Well, this is what we're going to do. For every mole of octane that's burned, we are going to produce 5,471 kilojoules of energy. So plus, it's going to be positive 5,471 kilojoules of energy produced. All right, that negative sign, we don't know. if the energy is being produced or if the energy is being consumed. The negative sign tells us that. Rather than using a negative sign, I'm just going to use a word. I'm going to just verbally say produce, so therefore I can get rid of the negative sign here. Just say this is how much energy is produced. You know, if somebody said, okay, how much money do you owe? Well, would you say, minus $10, I owe minus $10. Does that make any sense? No, you say, I owe $10. And so that's what I'm doing here. Yes, I look at my statement, it's minus $10, but when I look at it, it's 10 plus $10 I owe. A statement might say minus $10. It's the same thing here. And so then we got moles, and then octane. Octane is 12 of one's carbon. So 8 carbons, not carbon, 8 carbons. So that's 80, 9608. And then 18 hydrogens. It's going to be 1818. So what's this? 124. No, 114. Sorry, 114.26. 114.26 grams of octane per mole of octane. And so how many grams of octane we'll have to burn to produce this much energy? So let's punch that out. 9.05 times 10 to the 4th divided by 5,471 times 114.26. 890 grams. 1,890.06 grams. How many sig figs am I allowed? It's like 3 sig figs. So I could just say 1,890 grams. Or I can convert it to scientific notation. 1.89 times 10 to the 3rd grams of octane C8H18. That's burned. Here, I didn't need the balanced chemical equation. Normally, I wouldn't need the balanced chemical equation, but they told me, you know, it's this many kilojoules for every mole. So I didn't have to write out the balanced chemical equation. Anyway, they get the same thing, I think. They go from kilojoules to moles. Kilojoules to moles using delta H, to moles to grams using the molar mass. That's what we did. And they got 1,890 grams, or 1.89 times 10 to the 3rd grams. All right, that's the end of the chapter slides. But this chapter has one additional important topic we need to talk about. And so you'll see that when you get to the homework. Let's take a look at the homework problems for chapter 10. Get a general idea of the homework problems, the types of homework problems we encounter in this chapter. Oswald process is made, is used. This is one step of the Oswald process, which is used for the manufacture of nitric acid. So in this step, we take ammonia and then oxidize ammonia. Oxidize ammonia to nitric oxide and water. Okay, how many moles of ammonia would react with 95.3 moles of oxygen? So this is just a mole-to-mole conversion. You know, it's a 4 to 5 mole ratio here. So mole-to-mole conversion. How many moles of nitrogen monoxide would result from the reaction of 2.89. So another mole to mole. So this is moles of A to moles of B. We just use the balanced chemical equation to do that. And so all these are the same. Here we have the oxidation of hydrogen sulfide. This is another redox reaction. Essentially we burn it. When we burn hydrogen sulfide, we don't form CO2 in water. Do you know what we form when we burn hydrogen sulfide? We form SO2 in water. Anyway, how many moles of oxygen are consumed when 4 moles of hydrogen sulfide react? So this is just mole-to-mole conversion. In fact, all those are mole-to-mole conversions. Magnesium hydroxide is formed from the reaction of magnesium oxide and water. So here, this is nice again because they tell us the reactants and they tell us the product. And so we don't really have to do anything, but it's another mole-to-mole conversion. In our bodies, sugar is broken down by reacting with oxygen to produce water and carbon dioxide. How many moles of carbon dioxide will be formed upon a complete reaction of 0.424 moles of glucose sugar? So we need a balanced chemical equation for this, and then we can do a mole-to-mole conversion. That's a redox reaction, number 4, it's oxidation. 5, when sulfur dioxide reacts with oxygen, sulfur trioxide forms. This is another redox reaction. How many moles of sulfur dioxide? So again, mole-to-mole conversion. Number 6, aqueous solutions of potassium hydrogen sulfate and potassium hydroxide react to form aqueous potassium sulfate in water. This is an acid-base reaction, another mole-to-mole. So we just need the balanced chemical equation, but those aren't too hard because they tell us. We didn't have to predict. It's more difficult if you have to predict the products. Again, we're back to the Oswald process for nitric acid. Well, actually, am I going in circles here? No, I'm not. The previous one was a mole-to-mole conversion. So what we're doing here is we now have grams. So we got 268 grams of oxygen, O2. So now we're going to have to go grams of oxygen to moles of oxygen. Moles of oxygen to moles of ammonia, and then we stop because they're asking for moles. And so this is a gram of A to moles of A to moles of B type problem, but it's not, we usually don't stop moles. This is moles of ammonia, so we'll go from moles of ammonia to moles of water to grams of water. So these are all kind of halfway done stoichiometry problems. Some more halfway done stoichiometry problems. How many grams of butane can be burned by 1.42 moles of oxygen? Still, they're halfway done. This is all the way. This is a typical one, like this here. How many grams of oxygen are used in a reactor that produces 43.8 grams of water? So we're going to go from grams of water to moles of water to moles of oxygen to grams of oxygen. The mole-to-mole conversions using the balanced chemical equation. Here, C and D are typical stoichiometry problems. This one's typical too. So how many grams of CO2 will be produced by burning 78.4 grams of butane? So we're going to go from grams of butane to moles of butane to moles of carbon dioxide to grams of carbon dioxide. So standard, C and D are standard. Grams of A to moles of A, moles of A to moles of B, moles of B to grams of B type of stoichiometry. Number 9, the explosion of nitroglycerin is described by the equation. So this is nitroglycerin here, decomposes into CO2, water, nitrogen, and oxygen. How many grams of carbon dioxide are produced by the explosion of 21 grams of nitroglycerin? So this is a standard stoichiometry. We're going to go grams of nitroglycerin to moles of nitroglycerin. Moles of nitroglycerin to moles of CO2, moles of CO2 to grams of CO2. Standard stoichiometry. This is nitroglycerin dynamite here. And so this is a typical stoichiometry setup. Grams of nitroglycerin, and then we need the molar mass to convert it to moles. Then we need the mole ratio from the balanced chemical equation to convert to moles of CO2. And then we need the molar mass of CO2 to convert to grams. 12.2 grams of CO2 here. According to the reaction, 2 silver nitrates plus copper yields copper 2 nitrate plus silver. This is a single replacement reaction. This single replacement must go because they're giving us this reaction. In fact, copper versus silver, which one do you think is more stable, copper or silver metal? Which one do you think is more valuable, copper or silver? Silver. So this driving force is here. We're going from more active copper to less active silver. So we don't even need the activity series to figure this one out. How many grams of copper 2 nitrate will be formed upon the complete reaction of 26.8 grams of copper with excess silver nitrate? And so we start off 26.8 grams of copper to moles of copper to moles of copper 2 nitrate, moles of copper 2 nitrate to gram. This is standard. Soaps are produced by the reaction of sodium hydroxide with naturally occurring fats. The equation for one such reaction is this. So here's a fat with sodium hydroxide. We make the soap. This would be the soap over here. The last compound is the soap. Calculate the number of grams of sodium hydroxide required to produce 323 grams of soap by this method. And so we're going to go from grams of soap to moles of soap. So we need the molar mass. The molar mass of this is going to be pretty big because we've got 17 carbons, 35 hydrogens, actually 18 carbons. You got to add another one. 2 oxygens and sodium. So molar mass is pretty big. So we can see what the molar mass is calculated here. Yeah, 306.45 grams per mole, which is pretty big. So we're going to go from grams of soap to moles of soap, moles of soap to moles of sodium hydroxide. It's a 3-to-3 mole ratio. And then moles of sodium hydroxide to grams of sodium hydroxide. So that is your classic, typical stoichiometry problem. As is number 12. As is number 13. The same thing. This is interesting to know. One way to make sodium thiosulfate. Sodium thiosulfate, you know what the formula for thiosulfate is? Actually, I asked that. What does thio mean? Does anybody remember? Thio means replace oxygen with sulfur. So this is sulfate. Thiosulfate is replace an oxygen with a sulfur. S2O3 charge. 2 minus S2O3 2 minus. That's one way. The other way is you make flashcards. Another way is you write it down. So I don't care which way you memorize it, but you have to get it memorized. Thiosulfate is also a reducing agent. It's a common reducing agent. The advantage of doing this is there are other thio-type compounds that you can figure out based on replacing oxygen with sulfur. They're in the same family. But anyways, sodium thiosulfate is used as an antidote for cyanide poisoning. Wow. So what would be interesting is how it works. That would be interesting. One of the methods for manufacturing sodium sulfate used in the manufacture of detergents involves this reaction here. If you look at this reaction, can you tell what type of reaction this is? In a way, it looks like metathesis, but these aren't ions; these are molecular compounds here. It doesn't look like, well, it might be acid-base because there's HCl over there, but it turns out this is redox. I can tell this is redox because of the oxygen. Oxygen is 0 here; it's -2 over here, so definitely it changed. These 2 oxygens didn't change. But okay, another standard stoichiometry problem there. Hard water scum. Another standard stoichiometry problem. Except now we are dealing with milligrams. So milligrams, we've got to convert to grams. This is hard water scum here. It's a precipitate. It's hard to wash off. There you can see it. Trinitrotoluene is the chemical name for the explosive commonly known as TNT. This is its formula. The C7H5 part is electron rich. This NO part is electron poor. TNT is manufactured by the reaction of toluene with nitric acid. Toluene and nitric acid make TNT. So again, this is just standard straight stoichiometry. Pig iron. Straight stoichiometry. Solvay process, straight stoichiometry. Chloride, all these are straight stoichiometry. Let's see when we hit something different. So lots of standard stoichiometry problems here. Some of them we have to figure out the equation, like the combustion, others they give it to us. This is not. And starting with 31 here. The function of sodium thiosulfate, well, sodium thiosulfate was the antidote to cyanide poisoning, but it's also used in photography for developing film, removing excess sodium bromide, or silver bromide, sorry, not sodium bromide. What is the percentage yield if the reaction of 8.18 grams of sodium thiosulfate produces 2.61 grams of sodium bromide? And so 8.18 grams of sodium thiosulfate, so when we do percentage yield, we need the actual yield. The actual yield is what they actually got. And so this is the actual yield, 2.61 grams of sodium bromide. But in theory, how much should they have gotten? The theoretical yield is based on stoichiometry of the starting material. So if we have 8.18 grams of sodium thiosulfate, we'll go from grams of sodium thiosulfate to moles of sodium thiosulfate here. Moles of sodium thiosulfate to moles of sodium bromide, moles of sodium bromide to grams of sodium bromide. And then compare. That's, in theory, what we should have gotten. What we actually got was this, 2.61 grams. And so this is a percent yield type problem. Let's take a look. The answer here. And so the theoretical yield is calculated based on stoichiometry. 8.18 grams of sodium thiosulfate. So grams of sodium thiosulfate to moles of sodium thiosulfate, moles of sodium thiosulfate to moles of sodium bromide, moles of sodium bromide to grams of sodium bromide. So this ideal or theoretical yield is 2.66 grams. They didn't quite get it. It came out 0.05 grams short. And so they got 2.61. They should have gotten 2.66 based on the stoichiometry. And therefore they lost. They lost about 1.9% in sodium bromide. That often happens. So they got 98.1% yield. So number 32 is a standard stoichiometry problem. Grams of CO2 to moles of CO2, moles of CO2 to moles of butane. Oh, wait a minute, this is not it. Butane gas producing heat. When 4.14 grams of butane reacts with excess oxygen, the reaction yields 11 grams. So is this my theoretical yield or my actual yield? This is my actual yield. My theoretical yield is going to be based on how much starting material I had. So if I have 4.14 grams of butane, I go 4.14 grams of butane to moles of butane to moles of carbon dioxide to grams of carbon dioxide. That's my theoretical yield. And then compare the two. To get the percentage yield, I take my actual yield, 11 grams, 11.0 grams, divided by the theoretical yield that I just got from the stoichiometry. Let's see if this one has an answer here. No, it doesn't. Let me know if you want me to do the calculation on the board for any of these. This one's a little different because they give us the percent yield here. Calcium cyanamide is a common fertilizer. When mixed with water in the soil, it reacts to produce calcium carbonate and ammonia. The ammonia provides nitrogen to the soil. How much ammonia can be obtained from 7.25 grams of calcium cyanamide in a laboratory experiment in which the percentage yield will be 92.8%. 92.8%. All right, so the previous problems we were calculating the percent yield. In order to calculate the percent yield, in the previous problems, what we needed was the actual yield. The actual yield is given. That's how much you actually get. Divided by the theoretical yield. The theoretical yield comes from stoichiometry. Times 100%. And so, if we want to determine the percent yield, we do this. We need this. But sometimes we use the percent yield. So how much ammonia? Well, we're going to get a little bit less ammonia because we're going to lose some. How much are we going to lose? Well, if we have 92.8% yield, that means we're going to lose about 7.2%. And so we have to factor that in. Let's take a look here, this particular problem. And so what the 92.8% is this. We're going to have 92.8, this is by mass. So 92.8 grams over 100 grams. Okay, then we go, okay, 92.8 grams of what? And so it's going to be a product. Well, what is the product of this reaction? The product is going to be the product of interest. There are two products, calcium carbonate and ammonia. But the product of interest will be ammonia. And so we're going to get 92.8% yield of ammonia. And so the way we would do that here, we'd say there's 92.8 grams of ammonia for every 100 grams of ammonia. But then we have to add something to it. We have to add this, 92.8 grams of ammonia actual yield over 100 grams of theoretical yield. This is like the cookies, What did I say, 90%? Did I say a 90% yield of cookies? If it was a 90% yield of cookies, then we get 90 cookies actual yield over every 100 cookies theoretical yield. So this is the same type of deal. And so what we have to do is we have to add one more step to the stoichiometry. This is just a standard stoichiometry problem. And so we go 7.25 grams. So let's go with calcium cyanamide. Cyanamide is not one you have to memorize. Plus 3 H2O, water yields calcium carbonate, plus 2 ammonias. What kind of reaction is this? Can you tell? Very interesting. One way you can tell, this is not a metathesis reaction, so it's acid-base or redox. One way you can tell if it's redox is by looking at the oxidation states and seeing if they change. So calcium's 2+. What would nitrogen be? Nitrogen is -3. -3. That means carbon will be calcium is a 2+, then the cyanamide anion must be a 2-. So if nitrogen's -3, and we've got 2 of them, then carbon must be +4. Over here, carbon's +4 in calcium carbonate, nitrogen's -3 in ammonia, so no oxidation states change here. Oxygen's -2, hydrogen's +1. This is what we call a Lewis acid-base reaction. This one. I haven't talked much about Lewis acid-base. That's the Lewis acid-base reaction there. Okay, so what we're going to do here is we're going to go 7.25 grams of calcium cyanamide, and then we're going to go to moles of calcium cyanamide. And then from moles of calcium cyanamide, we're going to go to moles of ammonia. Then from moles of ammonia, we'll go to grams of ammonia. But this is the grams of ammonia theoretical yield. In theory, I should get this, but in practice, I get less because I lose some. And so this would be this many grams theoretical yield. Then I need one more step to get the grams of ammonia actual yield. And so the conversion to take the theoretical to the actual yield, I need this conversion factor. That is I'm going to get 92.8 grams of actual yield, 92.8 grams of ammonia actual yield for every 100 grams of ammonia theoretical yield. And so I just need one more step to my stoichiometry to do this particular problem. Hydrochloric acid is known as an enemy of stainless steel, the primary component of which is iron. The hydrochloric acid is going to attack iron. This is going to be a single replacement reaction here. Iron is more active than hydrogen, so this is driving force for this single replacement reaction. What will be the actual yield of iron 2 chloride when 3.17 grams of iron reacts with excess hydrochloric acid? So if 3.17 grams of iron react, we go from grams of iron to moles of iron, moles of iron to moles of iron 2 chloride, moles of iron 2 chloride to grams of iron 2 chloride. But that's what we call the theoretical yield. What's going to happen is we're going to lose some of it because this reaction only has a 76.6% yield. Actually, we lose a lot of it. And so we have to add one more conversion factor, that is 76.6 grams of iron 2 chloride actual yield for every 100 grams of iron 2 chloride theoretical yield. 35, the Haber process for making ammonia from nitrogen in the air is given by the equation. So we take nitrogen and react with hydrogen to form ammonia. This is not an easy reaction to do. Calculate the mass of hydrogen that must be supplied to make. Okay, so we want to make 5.00 times 10 squared kilograms of ammonia in a system that has an 88.8% yield. And so this problem is a little bit different. Is this going to be the theoretical yield of ammonia that they want or the actual yield of ammonia that they want? This is going to be the actual yield of ammonia that they want. And so, so we have N2 plus 3H2 yields 2NH3. And so what they want to do is they want to actually get 5.00 times 10 squared kilograms. So let's say you actually want to bake, you actually want 100 cookies. If you actually want 100 cookies, how many do you need to bake in order to get 100 if you have a 90% yield? You have to bake 111 cookies. And so this is the same thing. This is the kilograms of ammonia actual yield. And so I'd like to go from kilograms to grams. So we'll go to grams of ammonia actual yield. And then from grams of ammonia actual yield, we're going to go to grams of ammonia theoretical yield. Theoretical yield. And the way we're going to do that is this. For every 100 grams of ammonia theoretical yield, that's only going to produce 88.8 grams of ammonia actual yield. And so, in other words, we have to plan on making more, because this ratio is greater than 1, we'll have to make more ammonia so that we can lose some of it. And so, in theory, we've got to produce more ammonia and then lose it. Okay, so we need to produce this much in theory, and then we'll convert that to moles of ammonia. From moles of ammonia, we are calculating hydrogen. So we're going to go to moles of hydrogen. Moles of hydrogen, and then to grams of hydrogen here. And so there's one extra step. That one extra step is this one, with percent yield. We have to know. A lot of people, they don't know. They just take a 50-50 guess, like a flip of a coin. Which way they write this. They write it like this, or they write it upside down like that. Well, if they have the units, then they can tell which way they need to write it, because the units need to cancel. So this is what they did. Your book likes to keep it in kilograms. I like to go to grams. They're saying, if we want this many grams actual yield, they call it ACT actual yield. I call it AY. They want this many kilograms of actual yield, then they better be prepared to make more than that. So this is how much more. for every 100 kilograms of ideal or theoretical, they are only going to net 88.8 kilograms of actual. And then it goes into the stoichiometry. The stoichiometry is theoretical. Hydrogen iodide is a colorless, non-flammable, and corrosive gas with a penetrating and suffocating odor. It can be prepared by direct reaction of its elements. It is desired to produce 331 grams of hydrogen iodide in process with a percent yield of 71.1%. How many grams of hydrogen gas will be needed? So what we have to do is we have to determine this. Is this 331 grams of hydrogen iodide actual yield or theoretical yield? Actual. And so if we have that many grams of hydrogen iodide actual yield, then what is the percent yield? Write the percent yield as a conversion factor, 71.1%. .1% means 71.1 grams over 100 grams. It's by mass. So 71.1 grams of what per 100 grams of what? Yeah, hydrogen iodide actual over hydrogen iodide theoretical. So the 331 grams is what? Is that actual or theoretical? This 331 grams of hydrogen iodide. Is that actual? Yeah, that's actual. So that's going to tell us how we use this. And so we have 331 grams of hydrogen iodide actual yield. And therefore, I have to flip this upside down. And so that's 100 grams of hydrogen iodide theoretical yield for every 71.1 grams of hydrogen iodide actual yield. And so I just kind of make sure the actual yield cancels. That leaves me with the theoretical yield. Once I'm in theoretical yield, then I use stoichiometry to figure out the rest. Okay, calculate the percentage yield in the photosynthesis reaction by which carbon dioxide is converted to sugar if 7.03 grams of carbon dioxide yields 3.92 grams of sugar. All right, so in this particular problem, this 3.92 grams of sugar is actual or theoretical? This is actual. So what's the theoretical? In order to get the percent yield, I need the theoretical. And so what is the theoretical? The theoretical would be based on stoichiometry. So if I have grams of carbon dioxide, I go from grams of carbon dioxide to moles of carbon dioxide, moles of carbon dioxide to moles of sugar to grams of sugar. That grams of sugar will be the theoretical based on stoichiometry. And this is the actual that was given in the problem. So then the percent yield is the actual yield divided by the theoretical yield times 100%. And so let's take a look at their answer here. Their answer is, first, based on the reactant, how much sugar should we have produced? And so 7.03 grams of carbon dioxide, moles of carbon dioxide, moles of carbon dioxide, moles of sugar to grams of sugar. This is based on stoichiometry, the theoretical yield of the sugar. Based on the experiment itself, they only got 3.92 grams of sugar. They should have gotten 4.80, which means they got an 81.7% yield. Okay, this is the same type of deal here. This reaction yields 4.75 grams of ethane. The reaction yields 4.75 grams of ethane. Is that actual yield or theoretical yield?
Actual yield.
That's actual yield. The theoretical we're going to calculate based on stoichiometry. We're given 5.20 grams of ethene. Ethene's this. Both of these are redox here, so we go ethene to ethane. The other. Okay, so another determining the percent yield. Here we're going to use the percent yield. So this has a percent yield of 69.1%. How much acetic acid must be used to get 62.5 kilograms of ethyl acetate? And so this is what we want, actual yield. And so we're going to go from actual yield to theoretical yield. From theoretical yield, we're going to use stoichiometry to figure out how much acetic acid must have been used for that the reaction. Nitrogen monoxide is produced by combustion in an automobile engine. It can then react with oxygen to form NO2. NO is actually colorless. NO2 is this beautiful orange gas. If 5.74 grams of oxygen gas reacts with excess nitrogen monoxide in a system in which the percentage yield of nitrogen dioxide is 80.2%, what is the actual yield of nitrogen dioxide? And so here, from the oxygen, we go grams of oxygen, the moles of oxygen, moles of oxygen, the moles of nitrogen oxide, moles of nitrogen oxide, to grams of nitrogen oxide. That grams will be the theoretical yield. We're going to get less because we only get 80.2 grams of actual yield for every 100 grams of theoretical yield. So we're going to have to cut it down a little bit by using this conversion factor at the end. Here. Okay, let me know if you want me to go through any of these. Okay, these are just conceptual, limiting reagent, excess reagent problem. If the nitrogen and hydrogen react in a 1 to 3 mole ratio, so for every nitrogen I need 3 hydrogens, then which one's the limiting reagent, which one's the excess reagent? So I have 1, 2, 3, 4, 5, 6 nitrogens. I'll need 18 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I don't have enough hydrogen. Hydrogen is my limiting reagent. So this is just some conceptual stuff. Limiting reagent, excess reagent, conceptual. Here it is in terms of flask. These 3 flasks contain the same amount of HCl. And then you add zinc. When you add zinc, it forms hydrogen gas in a single replacement type reaction. In this flask, the reaction's done. And all the HCl's reacted. There's no more HCl left. But there's excess zinc. So in this flask, we have excess zinc. And we generate the maximum amount of hydrogen gas. In this flask, we don't have any more zinc left, but if you look, we've generated the maximum amount of hydrogen gas. So this flask 1 is excess zinc. Flask 2 is stoichiometric. We have just the right amount of zinc and HCl. So we reacted all the HCl, that's what produced the gas here, and reacted all the zinc. There's no more zinc left. In flask 3, all the zinc is gone. But we didn't generate that much hydrogen, not as much as those. So that means there must be some unreacted HCl here. And so HCl is the excess. And so over here, zinc is the excess, HCl is the excess, and this is stoichiometric. All right, now we're switching gears here. So let's stop. We're going to take a break, and then we'll continue looking at these problems here.